In this lecture, I'm going to prove a series of theorems establishing properties of limits that will allow us to compute limits without always appealing to the definition of a limit. So that actually the procedures that we will follow to find limits would be exactly the procedures that we followed in Calculus 1. And so the first theorem I'm going to prove is this one, that if you have a sequence Sn that is convergent, that has a limit, then you're guaranteed that if the sequence is interpreted as a set of numbers, then the set of numbers is going to be bounded. And to provide you with some motivation of this, let me draw a picture here. So let's say we're on a number line. We have some point S, or some number S, which is a limit of our sequence. And if our sequence Sn, if Sn converges to S, that means that starting from a certain capital N, all elements of a sequence should fall into this neighborhood. So that means that starting from capital N, the tail of a sequence is going to be a bounded set because it cannot deviate from S by more than epsilon. And then prior you getting into this interval, into this neighborhood of S, you have terms from the first one to the nth one. So that means that you have finitely many terms that might live outside of this set. But if you have finitely many terms, then that means that the entire sequence should belong to an interval that is bounded both from above and from below. All right, so that's the logic. That means that we have to treat the tail of a sequence separately from its initial few terms, because then the tail is going to be controlled by the definition of a limit. Okay, so let's then try the proof. I'm going to assume that a limit of a sequence Sn exists and is equal to some S. So then by definition of a limit, I can choose any epsilon, and then for that epsilon there exists a capital N, such that Sn minus S is less than epsilon if n is bigger than capital N. Well, then we can rewrite the circle statement without using the absolute value sign in the following way. And then if I add S to all three sides, then I'll get an expression like this. And it is going to be this inequality, actually these two inequalities are going to be valid whenever n is bigger than capital N. So then if I construct a set, capital Sn, in this way, I'll include in it all elements of my sequence with an index bigger than capital N. So that means n plus first element, n plus second element, n plus third, and etc. And for all those elements with index n being bigger than capital N, we know that Sn is bounded from above by S plus epsilon. So that means that S plus epsilon must be an upper bound on this set. And likewise, S minus epsilon will be a lower bound on that same set. Okay, so then if I look at the entire sequence contains all elements starting from S1 all the way to infinity. And I can split the set into a union of two sets. One is a finite set, a set that contains finitely many elements, capital N elements, and the tail of a sequence, capital Sn, that I already dealt with. So here union means that I'm taking a set which consists of all elements of capital Sn and the first n elements. So that way I recover the entire sequence. Well, because this set is finite, it contains finitely many elements. We discussed before that means that the set should be both bounded from above by the maximum of the set, maximum element, and from below by the minimum element. Okay, so then if from above the circled set is bounded by the maximum of the first n numbers, and the second set is bounded by s plus epsilon, then if I pick a larger of these two numbers, it is going to be a bound on both s capital N and this set. And likewise, if I find a lower bound of s capital N and a lower bound of the set of first n elements, I pick two lower bounds and I choose a minimum, and that would be a lower bound on both sets. So in that way, I can construct an upper and lower bound on the entire sequence. So if I take a maximum of the maximum and s plus epsilon, that must be an upper bound on the entire sequence. And if I take a minimum of s1 through sn and s minus epsilon, I'm going to get a lower bound on the entire sequence. But if I have an upper bound and a lower bound, that means that the entire sequence is going to be bounded. So once again, here I'm using the fact that if I took a maximum of n elements, and then I'll take maximum of that maximum and a new number s plus epsilon, then maximum of the maximum will just give me a single maximum. And likewise for the minimum. All right, so that's a first property, which is quite important, and we're going to use it later on a few times. In fact, we're going to use it today even, that every convergent sequence is bounded. All right, next theorem. Let's suppose that we have a convergent sequence so that we know that the limit of Sn is equal to S. And I have a constant that belongs to a set of all real numbers. Then we claim that if I multiply every element of my sequence by k, then Ksn will still have a limit, and the limit must be k times the limit of Sn. So when you take a limit of the constant times the sequence, then the limit is constant times the limit of the sequence. And before we actually produce a proof, right? So if I want to show that Ksn converges to Ks, then what I would need to do, I would need to estimate the difference between Ksn and Ks. Why would this difference want to be small? If I factor out K and then split the absolute value into product of two absolute values, I end up with something like this. Why can I make this guy less than epsilon? Because I know that Sn converges to S, so that means that I can make Sn minus S as small as I wish, and therefore K times as small as I wish will be less than epsilon. Now, to put some numbers associated with this, to write down some numbers, so I can solve this inequality for Sn minus S, and I'm going to get that inequality. Assuming that the coefficient k is not equal to 0, because if it is equal to 0, then this division is meaningless. So if I can somehow demonstrate that Sn minus S is less than epsilon or the magnitude of k, then I'm done. Okay, so let's suppose that k is not equal to 0. Again, I will fix some epsilon greater than 0. Then I know that Sn converges to S, so the limit as n goes to infinity of Sn is equal to S. And therefore, there must exist a number capital N such that Sn minus S is less than epsilon over absolute value of k. So before we had less than epsilon, but epsilon is some arbitrary number that you chose. So epsilon divided by absolute value of k is also some random small number that you chose. Okay, so we can pick this capital N, but then we can refer back to the idea above. So therefore, if I take n to be bigger than capital N, then if I multiply both sides of this by k, k times Sn minus S is less than epsilon. And then I can follow backwards the inequalities that I was doing here, because now if I know that ksn minus s is less than epsilon, I can combine two absolute values to get this, and I can distribute k to get that, but that basically means that I satisfy the definition of a limit. Because if I choose any epsilon greater than 0, there is a capital N such that ksn minus ks is less than epsilon. And that's exactly the definition of the limit of ksn being equal to ks. And so we proved this statement when k is not equal to 0. When k is equal to 0, things are even simpler, because if k is equal to 0, then ksn minus ks is simply 0. And 0 is less than any epsilon that you wish. And so we're going to proceed like this. We're going to choose any epsilon that you want. And I'm going to pick n, capital N, to be 0. Well, so if n is bigger than capital N, right? So basically, if little n is anything possible, because n is a natural number, so it's automatically greater than 0. Then what about ksn minus ks? This is 0 times sn minus 0 times s. This is equal to 0. Again, this is less than any prescribed epsilon, and so therefore the limit, again, is equal to ks. So that means that we covered all possible cases, and the theorem is. So I'll continue this in a moment.